can get the translation
I think
message.
the computations cost time, so it's
This dot, this, like this is what we are.
Yeah, how many hours when I was looking at some correspondence? Anyone optimize, so like sure I click wrong and if I respond to some that's perfect.
You can go to that message and get it.
And more
Like you can do this from
that means you don't really need to have it. We generate response.
So you want to make a subscriber to?
Yeah, that's one. But also, one is not that I don't think you can get like
do a software, you can write it to a file.
yeah.
Sounded like you said you just write it as well.
Yeah.
Increase the number of iterations, the performance adjusted.
Yeah, but those message, I don't, so I don't. Yes, that will be browse topic and first.
That looks good. Yeah, thanks.
Yeah, that's nice. We have to do automation. I want to get it.
I believe you, Anne.
You did the math.
You did the math, I believe you.
Wait, so you're saying that in that equation, they missed the
How do you get this?
Yes, you can say this is the paper.
You're right.
I don't know how to do it.
So you don't send out the equation on that.
That's what I was wondering. I was like, how does it land squared to nothing to nothing? It doesn't make any sense.
All right,
So we
everybody here? Okay, so we only have this room until 4:30, FYI. Let's see. So last time we talked about making maps with cartographer. I don't remember, Billy, is there specifically a lab for this topic? Is there a specific lab for running cartographer on your cart that's been released?
We've been using the EA write-up.
No, but is it an assignment for them yet? Or do they have that? Not yet. Okay. So at some point you will need to install cartographer. Again, it takes like 2 or 3 hours usually. So have a full battery. Maybe I'm exaggerating, but it takes what seems like a very long time. So I would encourage you to get started on that, and then also get started on installing the particle filter stuff after the lecture today.
So the next lab for the particle filter.
I think the next lab is more or less like you install these 2 things, maybe you can't I don't know. I'm teaching these 2 classes, but in general I'm not in charge of the labs, so you should ask me TAs.
Is it possible to create like a connector to make decent power supply for the car while you're not?
Yes, but it could be dangerous. So I know what you want to do.
Yeah.
I've done it.
But I'm a badass.
The thing is, the power board doesn't have anything like, so let's say you have your battery plugged in, and you have this cable plugged in, and you like switch over between the 2, I don't know what's going to happen. So, why would you do that? Well, let's say the battery's running out of power, but you'd like the board not to turn off, and unplug the battery and have something else take over really fast. Don't do that. But yeah, you could make one with a self-charger. I don't know. We have a bunch of. Oh, I know why not. Okay. So the board you have, the carrier board doesn't have the original power jack on it. But yeah, basically, if you really want to do it, go talk to somebody like Sid or somebody in lab before you do anything like that. Okay, so today is sort of like part 2 of our localization and mapping lectures. We're going to talk about particle filters. And to sort of set the stage, the motivation is that cartographer is kind of too slow if you're going at 10 meters per second. If you already have a map of the world and told you the world was static, why bother making another one all the time? So here's the problem setup. You have a car, it produces laser scans. Okay, we all know this. You also have a map and some odometry. So where are you getting the map from? This is an easy question. Cartographer previously. Yes, it's occupancy grid.
Or the TA gave us.
Pardon?
Or the TA gave us now.
Oh, I'll talk with them. Could be a while. So then you also have some odometry. Where's that coming from?
Yes.
Good. Okay. And our goal is localization, which means we want to know the robot's pose in the map. Okay? Everybody's good on this. We're not making the map, we have it. We just want to know where we are. Okay, so input, you have your laser scan, here's this room. Then you have some control input, right, which gets reflected in what? The vehicle's odometry. Okay. So, has anybody ever tried to localize their, localize their robot just by keeping track of the control inputs? How well does that work? Not good, right? Is it useful? What are some of the problems that you have in scan matching? Why does that happen? Like on there's certain parts of the map that can do very poorly on. All way, right? So, but if you knew the robot had to be moving because you had your odometry, that would be helpful, right? So, then we have some map. But the idea is to use all of this information together to get a better answer. Okay? So the output of this algorithm that we're going to talk about is two things. So the first, which is obvious, is the pose of the robot on the map. And the second, which is sort of a side effect of the algorithm, is a bunch of guesses about where the robot may be, which represent a distribution of possible poses. So it's the robot's belief about different places that it could be. And in particular, in this algorithm, it can be multimodal, right? It can say, I'm either here or here. And that was sort of the big deal about switching to particle filters, Kalman filters. So this is pre-cartographer on the right. You can see that we didn't get loop closure, but it kind of works anyway. That's where, I mean, in terms of where we got the map, but this is sort of a synced front view camera of the robot driving around the MLS hallway, and then the particle filter right. And you can see that, like, we're seeing the floor occasionally, the map's not perfect, and yet this is still working. So the particular implementation that you're going to use is pretty robust, and that's why we like it.
Is this an older LiDAR? Like looks like it doesn't have as much.
It's both older and it's slightly tilted down and it's seeing the floor. So everything is wrong. And it still works. Which is a good thing for any algorithm that's going to run with the robot. Mostly. Okay. So I'm not going to go crazy on the derivation of this, but there is some background that I want to make you aware of. When I post these slides at the end, there's extra slides that talk about how you derive these equations if you wanted to. But probabilistic robotics, that's your book. You should have a look at that. If you go on YouTube, I'll post a link. Well, from one of the authors of that book recently gave a guest lecture at Berkeley in Peter Beal's class on particle filters as well. It's like 1.5 hours. And you could watch that if you're excited about the segment. Okay, so particle filter, another name for it would be a phase filter. And so the key idea is that we've seen some data, right? What's in our data? What are the two sort of things that we have? Predominant laser scan? Yeah. Okay. And we have some prior belief about the world, our map. And what we want to know is this conditional probability. What is the probability I'm at this point in the world, xt, given all this data that I've seen? Okay, so it's a simple enough idea, right? It seems a little crazy though. How do you implement any of this? Like, what is the probability distribution associated with this question? It's not trivial, right? So here's some notation. So we have p0. This is the data as a vector from time 0 to t. Okay. Xt, that's the robot state that we're interested in at time t. And in the books, you'll often see this listed as BEL, or belief. It's the conditional, just this conditional probability. Another fancy word to confuse you, but it's simple, right? All right. So, like we said, there's two sources of data, and we should probably actually distinguish between them because we're going to have to treat them differently. So there's some data that is perceptual, right? This is just your laser scan. These are things that, you know, are like static observations of the world. They just are. And then there's other data that I would say is like, that sounds interesting, control inputs, right? Your odometry data, which tells you about the robot's motion. And so, I don't know if anybody's seen something like this before, but this is usually how you would describe a trajectory. Okay? So we have some perceptual state, we have an action, which leads to a new state, right? I was going to put this in reverse, but, right? We're going to distinguish between those two pieces because we're going to have two types of models associated with them. One model is the robot's motion model, right? And the other is the sensor model. All right? So it's going to become very clear why we have our map formatted in this particular way soon. And the motion model, more or less, is chirping in this case. Okay. So again, perceptual observation, odometry, or like your sort of control actions that describe the robot's motion, and then you just have a big history of this. Okay. Is there anything special that you could maybe do if you have like a long history buffer? Something you could say about the process that generates it? Property. Yes, Markov property. Right, could help you here. And if you go through the big derivation, you'll find that in simplifies things. So does that, can you give a definition?
Like your next state depends on your current state and not the previous one.
Yes. So it's sort of like your current state somehow encodes all of your past history. It doesn't matter what you were doing before as long as you know sort of your belief about it. Okay, so this equation is gigantic. I tried to also make it gigantic on the page and give some hints for reading it. I think I prefer to read this from left to right. So what we're starting out with is our previous belief, right? And so when we begin, we have no idea where we are, right? You could pick uniform over the whole map, or you could ask the user to click a point and just draw particles from a Gaussian there, right? So it can be uninformed prior, or it can be something better, like if you make the user click a state to start. And I'll tell you that in the implementation of software, that's what's going to happen. Okay. So you're first going to draw some particles with replacement according to their importance weight, right? Equivalently, just sample from some base distribution that you're interested in. Okay. Then for each of those particles, you're going to need to simulate them according to your control input, right? So you pick some initial guess from some places in the map, and now you're going to apply the motion model. So you know that you told your robot to do this at the next time step, and this happened very fast. So probably your robot's sitting here, and you're going to say 0 because I didn't steer the car or tell it to drive anywhere yet, right? So the particles just stay where they are. But in the future, maybe you're shifting them forward according to the cosine x, v sine x, right, theta, so on and so forth. Okay. So according to this, right, this motion model, imagine that you drew these particles from some known distribution, you would be able to tell me what is the probability that I got to these new states given my action, right? Very easily. Is that clear? Okay. But what we need to do is integrate out over all these previous guesses, right? And so essentially we do that, and then we're going to update these particles again, their weights, right, before we resample them according to our observation model, right, our sensor model. So that's this one right here. Okay, so we got to all these new states, and I want to know, given what my, right, so we did an action, right, this is sort of an assumption that these things are proceeding sequentially, right, we did an action, so we had some guesses about where we were, we applied an action to every single one of them, right, that got us to a new state for every single particle, okay, and then now we got a real observation from the car, but we also can get a fake observation from every single particle, right, this is P OT given xt, right? This is how likely is it that I get this particular observation from the world given my updated particles. And then since we're talking about the posterior or probability, additional probabilities do come from a probability distribution as well, we need to make sure that everything stays nice and normalized. So there's some constant eta that goes in front of all this. Right, so this is sort of the mathematical view of it, but actually implementing this algorithm is quite a bit simpler than this equation looks like, except for the sensor observation model. And just to be clear, like we are one of the really key things here, right? You could decide that you are always just in some Gaussian around whatever your odometry says, right? Something like that, right? But if you're in a long straight hallway and there's an identical one around the next corner, right? It's really the case that you could be in either one. And so the sort of clever thing about the particle filter is that it doesn't assume how many modes your distribution has, right? You're representing the distribution by particles, so really the only limit to the number of modes is the number of particles that you have. I don't know if it's super clear right now, but it's a very useful feature of this approach. The penalty is that you're going to want more particles, and then for every single particle that you have to do this forward simulation of the motion model, and you have to do the simulation of the sensor model, right? So it grows linearly with the number of particles, for sure. And it's also quite dependent on the size of the robot state and complexity. And so, again, can anybody see why we're using this for localization only and not localization and mapping? Of course, there are some that do use it for SLAM, but why wouldn't you like it, maybe? Sorry?
Computer?
Well,
Matching each of their scans to
not quite. It has to do with the state.
If you're saying the state's the entire map, you have to do it for all the points in the map.
Every waymark, yeah. So right now, the state is just x, y, theta. It's very small, right? But if I make my state also my belief about where things are in the world, right? And I'm representing that as, pixels on a grid, or worse, just like every laser scan, all the points in every laser scan that I get, and the state's going to be huge. And it will be dependent on the size of the world that I'm exploring. Okay, so pictorially, what did we say in this equation, right? This is some map we generated of MLab using cartographer. I actually just put the car on the table and aimed it around the room. This is really good. I promise real cartographer is better than this junk up here. Okay, so the first thing we're going to do is we are going to sample some potential poses of the car in the map. And we're going to do that based on some odometry guess or odometry pose, so either user supplied or just from the desk. I encourage you to supply this. We had one team spend the entire semester, they didn't figure out how to run BNC on their car, so they never could click in RViz when the car was running to set initial guess for the pose, and they couldn't figure out why their car wasn't optimizing quickly. Don't be that team. Right? So you make this initial guess, and let's say that this particular implementation of the algorithm draws some set of particles around it from some Gaussian distribution with some variance of like 1. Okay, so we have all these particles. And you're going to give some control input to the car, either from your handheld little joystick thing or your algorithm. Okay? So we don't know which one of these particles is right. So what happens? We're going to forward simulate all of them based on the motion model. Okay? So you apply the control and you update all the poses of the particles. All right. Okay, we have an occupancy grid. There's a very nice thing about having a planar laser scanner and an occupancy grid that says what free space is, because just like in Cartographer, where they can update the grid based on where the hypothetical ray would pass through, we can also simulate the LiDAR pretty efficiently from any point in the map. Okay? So for all of these particles, we can raycast into this map and simulate a fake LiDAR. Go ahead.
Do we simulate, like, our LiDAR gives 1,000 scans or something? Do you usually simulate all 1,000, or do you, like, how many do you have to do? To
No,
make it work?
so we'll get to sort of the tuning, but this thing I think uses about 150 or something. So it's usually smart actually to subsample the LiDAR so that you're not so sensitive to noise. So that's one of the reasons that you see, in that previous video where everything is kind of wrong, things are still working. One of the reasons is because we're subsampling the LiDAR, which helps. Right, and note that this is not like scan matching where you're coming up with one best answer. You have hundreds, thousands of proposals, and the goal of this algorithm is just to rank all of them, essentially. So it's going to pick the one that best fits the data, not an exact match necessarily, just to be clear. Okay, so how hard do we think this updating the sensor model is? What can we say about it? All right, 2 questions. So between 2 particles, particle 1 and particle 2, is there any sort of interdependence on computing their scan, their fake scan? Is there any reason I have to do particle 1 before particle 2 or vice versa? No, right? Do we think that's a positive or a negative thing? Positive, good. Okay, so as you know, there's a GPU on the car. So this algorithm is one of the most embarrassingly simple to parallelize things in existence. So not only do particles not depend on each other, individual rays in each scan don't depend on each other. Although there may be useful information, like if you were more clever with your kernel. But yeah. So go ahead.
When we're using the GPU, we still have to send each iteration before we go to the next iteration, right? Before we go to the next iteration.
There's some overhead, right? But let's think back of the envelope. Like if I have 150 rays per particle, and I have 4,000 particles, I'm asking the GPU to do a pretty significant amount of work. Okay, so you're going off of like your normal x86 sort of memory model, as far as I know, where yeah, it's right to think like, is it worth sending this stuff to GPU memory and shipping it back the answers? And even in the normal case where that's expensive, I think this would be easily worth it. Right? That's one of the main pluses of this approach.
But we have to like sync all the threads before we go to the next iteration.
So you don't have to do this, somebody has done it. But
In like theoretical.
in general,
sync before we go
you
to
do
the
need
next.
to sync. Yeah, I don't know. You could do an anytime version of this probably. Right? You
But
could just
we
say
only
I have some
compare-
time window, right? And I'll take all the ones that I get back and then just stop when I run out of time. You can still use those results in your normal life. I don't see why you couldn't do that.
How would you be able to rank different articles which are not from Ireland?
Okay. I'll come back, but yeah, we're going to score the particles like this. So we have a real measurement, right? And so this should look really familiar. This looks like a Gaussian, RDF kernel, right? So you just have some score between your real scan and the fake scan you got that is based on the differences of each ray individually run through this kernel. Okay? So what you're saying is very intuitively correct, right? If we want a probability distribution, we just throw away some of our guesses, like how do we expect everything to add back up to 1 again?
If they're not from the same
yeah.
time period.
Yeah. Oh, well, so it always will have to be from the same time period.
Yeah,
You can
that's-
early stop,
Yeah.
right?
But we have to make sure all of them are in the same time period. according to the
Correct, yeah. Yeah, so if you're using a queue, you need to have something to like clear it
before we stop it.
before you start it on anyway. Okay, so, go
Why
ahead.
did you need a Gaussian there? Why couldn't you just take the mean square?
So you can choose many distance metrics here. I don't see any reason why one would be less or more valid than the other, but if you go read more afterwards, it turns out that there's some things that you want to do to this metric to make it work well, and it's morally equivalent to this Uber loss that I was telling you about the other day, where you don't want to be too sensitive to outliers. Like, you do not want a spiky sort of loss landscape here. You want it to be smooth. Sorry, that's not a good answer, but there is a link at the end which tells you how to tune up this distance metric. I didn't think it was very relevant because it's already tuned. So it's way harder to compute this sensor observation model than the motion model. I hope we all agree on that. Like, doing an update to 3 differential, very simple, different, like motion model equations, differential equations, right, in discrete time is trivial, even if it's for 10,000 particles. But once you say that every particle has, 500 beams associated with it, and you have to do raycasting, this is a lot harder. This will be the limiting factor in terms of how many particles you can run and still keep the sort of execution time reasonable. Does that make sense to everybody? Like, orders of magnitude difference in different particles. Okay, so there's some really efficient methods for coming up with the simulated laser scan. So there's essentially two or three versions that are implemented within this package. So there's one called Gresham's line. If you've seen it, you're basically trying to find the biggest circle that you can fit that doesn't collide with any part of the wall. So you know you're safe to step that far, right? And then you keep doing this over and over again. So imagine that you were forward simulating this ray and you wanted to find out exactly where it hit. You would want to take huge steps and then tiny steps when you got to it. This accomplishes that. There's another version called ray marching. We won't get into the details, and you can also pre-compute signed distance field for your map ahead of time. You'll be using the ray marching GPU implementation. It just runs really fast on So as I was saying, we have some real scan from the car in green, right? That was at some XT and your actual pose, right? And then we have all these purple fake scans that are at hypothesized XTs based on your motion, applying your motion model to your particles. Okay? So each one has some fixed number of beams. Let's say they both have 100, right? So I have 100 of the green beams and I have 100 times the number of particles of the purple ones. And I want to evaluate for every particle, like how close was it? How well does this particular observation match the one that I got at my actual state or repeat observation given XT? That's what we want to compute. Okay, and so the way that you can think about this is that we have some distance function or metric function, which could be like a RBF kernel. Okay, this is what this is, where we have OT, which is our actual observation, and then the range measurements from particle I, and you take the point-wise difference between them, right, and then just take it on. Okay. So in code, here's how this ends up looking. Can people see this? It's a little small, sorry. So we have some total number of particles, M, and for each of these indices in the set M, we are going to sample a particle, right, according to our previous belief about the robot's pose, right? So in the beginning, this could be uniform, or it could be Gaussian, right? It doesn't matter. Okay, and then we're going to get another argument to this function is whatever your control action was. Okay, so the next thing that you're going to do is for this particle that you just sampled, you're going to compute where you think it would have been given that this was your action, right? Okay, and then we're going to simulate the LiDAR for the new pose, and we are going to update the weight of the particle according to that RBF kernel that I showed you. Okay. Okay. And so then we're going to add this new pose guess and weight to the distribution, and note that there's no reason that these weights have to sum up to 1 right now. But what we can do is just add them all up, right, and divide every single weight by the total, right, then they'll sum to 1 here. Okay. And so here's how this goes. This is the sort of inner loop, and then the outer loop is, well, true. So while your robot's running, get your last odometry and get your last sensor reading, feed that to this MCL algorithm I just showed you. Okay, so one of the reasons that particle filters are great is, the math might look a little bit complicated, maybe depending on your level of how comfortable you are with probability theory, but they're extremely simple to implement. Right? The framework for doing this is very general, right? And you can use it for lots of things other than just localization. Right? So if you want to track other cars, use a particle filter. Right? And even in image space, you could do this, I think. So it's a good tool to have, and I would encourage you not to be scared of them because they're simple, and they're awesome because they're very embarrassingly parallel and everybody has GPUs these days. So is this helpful? Or I hope this is pretty clear so far. Okay. So like what I showed you, right? This is going to keep happening over and over again. One thing that some people do, and this is quite effective, is that they'll divide the samples they have into quantiles, meaning they'll say that this is a top 10% sample. Well, this is like one of the 10% worst, okay? And you can throw away the really bad ones, and you can redraw from your distribution new ones to replace them, okay? So this ends up, what happens is as you go along in time, you'll find that all the probability mass will concentrate unimodally around where you actually are. So this just can help with the efficiency. It can also be problematic, right? So let's say that it picks the wrong hallway, right, and your environment is absolutely symmetric. Okay, can it ever recover from that? Not easily. Some people will inject noise into the particle filter periodically to maintain the exploration part. And so, yeah, there's a lot of tricks associated with this. In particular, there's a very nice set of lecture notes from Drew Bagnell, who's currently ECTO at Aurora, called Particle Filters, the Good, the Bad, and the Ugly. And I encourage you to check it out because the answer is that they're mostly good. And there's fixes for the bad parts. Okay, so you're going to download this repo from us. You may already have it, I'm not sure. Hey, Billy?
Yeah.
Is the, it's on F1TENTH, but you probably haven't downloaded it, right?
Yeah, it's in a separate repo.
Okay, so the same place that you've been getting all your other skeleton software, github.com/f1tenth.org, there is a repo called Particle Filter, I think, and there's also a repo called rangelibc. You'll need both of those. So you're gonna pull this software. I believe that we have updated it so that you don't have to change stuff in the build script anymore. We'll double check. But there used to be a thing where, depending on which version of CUDA you had, or which, if you have TX1 versus TX2, you have to go and edit the build script, or MVCC would fail. But I believe we fixed that. And we've also made the output of the particle filter a bit nicer, so we give you an estimated covariance for your pose as well. So in this folder, there'll be some launch files. One of them is called localize.launch. You're going to give things like the number of particles that you want, anywhere from 250 to 10,000 is reasonable. For this next race, I would leave it as where it's at. However, in the future, you may find other uses for your GPU, for your projects, and running a large number of particles may not be feasible anymore. And in Billy and I's experiments, we've got it to work with only 250. Second, there's this angle step that downsamples your range measurements. Again, the current value is good. You could play with it if you want. There's a squash factor. This thing is basically smoothing out the particle weights. And then there's a bunch of different methods that you can choose from. Choose RMGPU. That's the best one. And there's also a max range setting. So this says, I won't care about LiDAR measurements that are longer than this particular range. And so your LiDAR can see 30 meters. But there are some cases where you're driving is not perfectly flat. And if that happens to you, I would recommend reducing the range so that you don't keep seeing the floor. In MLab, you don't need to do that. 30 meters is fine. 20. There's also a map server.launch file. You'll need to edit this, and you're just going to change this your map portion to the name of your map. It's pretty simple. Okay. So here are some additional resources that you can check out, and I'll post the slides shortly. I think that, yeah, especially this Drew Bagnell, particle filters, good, bad, and ugly. Very short read, very useful. This Corey Walsh and Sertaj Karman paper, they are the original authors of the GPU-based raycasting stuff. And so they compare all the different methods. If you're interested in knowing how they implemented the GPU part, it's a good place to look. If you like watching videos, there's a Udacity video on this with some exercises in Python. The reason that we're not having you implement this from scratch is that for it to really be useful, it has to be really fast, and we're not going to teach you the class. There is a class at Penn on CUDA. You can take it. One of the projects could be scan matching or particle filtering. Somebody in our lab did it. But this video is pretty good if you want to hear it from Sebastian. It's very simple. So yeah, that's it for me today. What time is it? You have about 40 minutes here, and we have to get out early because of senior design. So I'll be around, but my strong recommendation would be if you're not like getting crushed in your other classes right now, and you have some time, get this software installed and start trying it out ASAP. It's not hard. All you have to do is download the packages, and if something doesn't work, we will help you fix it. That's not your job. And then I think next week we're going to cover Pure Pursuit and some motion planning stuff, and that should get you pretty close to being ready to race.
The week after that is the week. Spring break? Spring break.
Yeah.
Yeah, so it's going to have to be the week after.
Is that after the week after spring break?
Yeah, whatever happens, I think, Billy, there was a request that it was after spring break.
Huh?
There was a request that the race is after spring break.
Yeah, it is.
So we should do that.
Yeah.
If we somehow have a dead class, we have a good topic for it.
So we don't have a lab that's due next week, Wednesday.
I mean, you're gonna need it for the next lab.
I mean, like the cartographer stuff is basically what we need to do.
Yeah, so if you don't do it, then you will have a much harder next lab.
Yeah.
And it will be very frustrating to be trying to solve issues with these two things at the last minute. It will be
Oh,
uncomfortable.
so the particle filters is pretty much all fully.
Correct.
Oh.
Yeah, you just need to install them and make sure that they work. And there's a bunch of dumb things that could have happened in the car that really are not your fault. Like if you, for example, connected the motor backwards and you're multiplying the velocity by -1, right? Like, okay, mapping doesn't work. Why? Well, we can help you, but you need to know sort of what the bugs are. Yeah. You just have to try it out. Yeah, so that's it for my lecture today. I'll get these posted. Is the preference on Piazza or Canvas, right? Nobody's told me.
Canvas. And then you can download everything at once.
I see.
Should we download everything? We won't have time to download it here.
Yeah.